All right, so we're going to start our next unit, first one of this second semester. I wanted to just kind of tell you I took a look at 6 past AP multiple choice exams and pulled out all the problems relating. I pulled out all the problems relating to each unit. And this one, I just did this yesterday morning, and I'm adding to this this packet, because there were a lot of problems on the tests that pertained to this packet. So there was a lot of things related to this probability of this thing called these random variables and finding their mean um, and learning how to do that in sampling distributions. So anyway, so this is a really important packet unit. Lots of questions on the test based on this unit. So we're going to start here today about random variables, and we're still in probabilities of things, okay? And we're going to be finding their means and standard deviations. And we'll do our homework pages 6 through 8 today. So that's where we will end up. All right. So I want you to take a look at your packet, and actually, I think this is page 1. Let's take a look at this. This should look familiar. We did this activity last semester. And so I want the odds to tell the evens. I will tell you we were flipping the coins for heads. Odds tell the evens what was happening in this lab that we did, and what did we kind of come up with. Okay? Talk for about 30 seconds on that. Go. Hey, thanks. All right, so let's see. Maddie, what did you guys say? Odds told the evens. So, okay, go. Who's the even? Okay, go.
So every time you do a trial, you add a number on the denominator, and then if it's heads, you add one on the numerator. And it's supposed to get closer to 50 because, like, the law of large numbers.
Very good. Very good. So what happens is this lab was collecting our experimental data. Okay, this is what was actually happening when we were flipping those coins. And did everybody end up at exactly 50%? Not everybody, but a lot of us were close to 50%. And the further you got away from 50%, the less people there were. We had kept track of that. And so what we found was, as you do many trials, then this experimental data will really kind of settle down to the true probability. Now, what's that called if I expect it to settle down to, in this case, 50%? What kind of probability is that? Not experimental, but what? Theoretical, yeah. So theoretically, here is what should happen. Okay, so we know in the long run, our experimental is going to settle down to the theoretical. All right. So this is just a little review, because this is important to all the probabilities we do with our random variables. So turn the page and let's take a look at our random variables notes. So let's talk about what a random variable is. All right. So in our previous example, flipping a coin, so the result that you get when you flip a coin is our random variable. Do you know what's going to happen on the next flip? No, you do not. It is random, okay? And it is a variable because I can be talking about the result on the next flip of a coin. I can talk about the result on the next deck of cards. It's going to vary from trial to trial, and it is random where I can't predict it. Now, we know based on law of large numbers that in the long run, it's going to settle down. All right. So we want to talk about also, here's some other examples of types of random variables. So a variable could be if X represented the number of boys that you have in a 3-child family. So what could that be? What are the options? How many boys could you have? 1, 2, or 3. You could also have 0. Yeah. So when I look at a family of 3 children, do I know how many that boys have there are in that family? I do not. It's random and it varies from family to family. Hence, are random variables different from family to family? How about this? Defective light bulbs in a case of 100 bulbs. Do I know how many light bulbs are defective in that case? No. So I'm going to look at case after case after case, and the amount of is random. I don't know. Okay? It varies from case to case. Now, law of large numbers tells me what? In the long run, what am I going to be able to do? And in the long run, I will then know what? On average, about what? The average number or the probability or the whatever of that I have of the number of light bulbs defective per case. Okay, how many I expect to be defective. All right, so there's just kind of some examples. Now, we have already talked about discrete versus continuous before. So I want to give you about I'm going to give you about a minute because I want you to kind of sort through what all this is a lot of kind of wordy stuff. I want you to sort through this vocabulary and think about what it's saying. And then I'm going to have the evens are going to tell the odds. They're going to translate this in kind of regular words, but you have to read and think for a minute. So go. Okay, time's up. So evens tell the odds real quick. In your words, the difference between discrete versus continuous. Go. What do you think?
Discrete is ones that like you can count, and there's only like distinct values. There's no like variation or like there's no like unlimited possibilities like with height and weight because that's continuous. It's like you can have any sort of value.
Gotcha. Not unlimited amount. Good, got it. Okay, good. Okay. So let's see how you did. Discrete is a set number of outcomes. We're going to play a game shortly, and there's only 4 possible outcomes that could happen. Hence, it's discrete. It's a countable amount of options that could happen. All right. So let's see. If we were talking about, like in this, the number of patients in a doctor's surgery, that, okay. I'm like, is it not one? I don't know. Are we frequently multiple? I guess if you're doing organ transplants or whatever. Okay, that's weird. How about, I like this number of defective bulbs in a box of 10. You're either going to have 1 or 2 or 3 or 4 or whatever, wherever it ends up being. I don't know. 1, 2, 3, 4, 5, 6, and so on. So that's kind of your binomial situation where you have that discrete amount of finite possibilities, as opposed to, if we were talking about the weight of something. You could have a little weight and a little teeny tiny weight next to it, or the amount of, say, carbohydrates or grams of sugar. You can have that in finite little bitty measurements where it's so small that it's making this continuous function of all of these possibilities. Okay, so there's that. Now, I want you to go ahead and talk amongst yourself as to whether or not these 4 examples are discrete or continuous, and so do that now. Go.
Are we supposed to do the bottom ones too, or just the top?
Just the top 4.
What's the Bucky shirt? It says, since don't mess with Texas, considered a winner. It looks like a Kroger.
All right, time's up. Let's see what you came up with. What do you have to say about the number of desks in a classroom? Yeah, discrete. There's going to be a finite amount of countable options. Okay, so that's a discrete. Now, I want you to think about it this way. Here's another question, though. What if I changed it to this? The average amount of desks per classroom, the average amount of desks per classroom in a high school, the high schools across Texas. So I would get an average from Aledo High School, an average from each Fort Worth High School, an average from Weatherford High School, and so on. What are those numbers going to look like? Continuous, because those averages can be all these little infinitely many small amounts. All right, you see how that can change? All right, fuel efficiency, miles per gallon. Those are going to be little small, tiny finite amount or infinitely many amounts. Distance a person throws a baseball. Continuous, same thing. How about the number of questions asked on the final exam? Discrete. But if I go to my Facebook page and I go to different College Board stats academies across the nation in the summer, and I say, what's the average number that this one has on the final exam, the average number of questions these teachers have on the final exam, the average number of these California teachers, the average number of these Texas teachers, those averages of the discrete is then what? Your continuous. Okay, let's take a look at these possible, it's a sample set of all possible values that could happen for, now these are discrete, so there's a countable amount of options. So, do you know how the World Series works and games and stuff? A lot of people may, but anybody who doesn't know how the World Series go? Okay, so yeah, let me explain that to you. So the World Series is going to be 2 teams. Last fall it was Astros and Nationals. And they go and they play the best up to 7 games. So they're going to keep going until 7 games. And so basically, when do you know you have won the World Series? If once a team has won 4 games, then they're done. Okay, because in the end, somebody's going to have 4 and somebody's going to have 3. So once somebody's reached 4, they're the winner. Okay, so minimally, if you were going to go buy tickets, they announce the 2 teams and it's your home team. And how many games do you know it's going to go to for sure? No questions. 4. Because if, say, it was the Astros won all 4 in a row, then the series would be done. But there's at least 4. If they lost one of those, then it's going to end up going to what? 5 games, because they have to play another game to possibly win, and so on. How many games? It also could be have to go to 6 games. But what's the most amount of games that would be played to reach that 4 wins, 7. The last World Series, anybody know? It went to 7. It was very interesting because the Nationals won at the Astros home field. So the Nationals won, and then the Astros won at the Nationals home field. And then guess what happened in these last? You're back at Houston, and the Nationals won. So that was interesting World Series because nobody won at home. Anyway, okay, just a little tidbit of information. So do figure out what the set of possible outcomes are for each of these others. Okay, do that for a minute. Mm-hmm. Okay, I'm going to stop you there. How many heads can you have when you toss 2 coins? 0, 1, or 2. Good. How about having a 5-card hand? How many hearts could you have? 0 up to 5. Okay. Now, what about you sum together the dots on the top of a pair of dice? So you're going to have 2 die. What's the lowest you could have? You could have a 1 and a 1 for a sum of 2. And then all these different possibilities. What's the highest you could have? 6 and 6. Okay, so the highest sum could be 12. So we're going to actually take this over and do it a little bit more in depth and talk about the probabilities of each event. So let's skip a few pages over to page 5. And you will see this problem that is talking about a pair of die that is being rolled. Pair of fair dice. Fair. All right. And X is the sum of the dots on the top faces. Is that going to be a random variable? It is something that you don't know what's happening next. It's going to be random, okay? And so it's varying from roll to roll. So we are talking about the sum of the 2 faces. All right. I want you to take about 30 seconds and read this right here to these 2 sentences to yourself so you can understand what these numbers here mean. Okay, go. Okay, so now somebody's going to tell somebody something. Let's see. Let me pick who's going to do it. I want the evens to tell the odds, the interpretation of that number right there. What does that mean? Go. What do you think that means?
It means you get a 4 on the first die, a 3 on the second die, and a sum of 7.
Perfect. Good job. Okay, so let's see what we came up with. So evens told the odds. So the odds tell me, Lily, who's odd over there? Okay, what you guys come up with? Go, Maddie. 4 on the first row. 3 on the second row. For a sum of 7. Very good job. That is exactly right. Okay, now the odds are going to tell the evens two different things. And we're going to look at this number here, this set of number here, and this here. So the odds tell the evens. Something that is different about these two and something that is the same about these two. Go. Odds are telling the evens. Okay, so let's see what you come up with. Odds told the evens. So the evens, who's got that back there, Miriam? Okay, tell us what you got. Difference between these two things.
So basically what the difference is that which die got which number.
Which die got which number? Good, that's different. The order in which those values occurred. Good, what's the same?
The sum.
The sum. Yep, they both have the same sum of 3. All right, let's go ahead and up here on this top row, let's write what those possible sum of the two faces are. You told me on an earlier page, what are the possible outcomes? Sums. What could the first one be? 2, and so on. 3, 4, and fill it in. Okay, now what we want to do is we want to write out a probability distribution. Probability and likelihood of these occurrences. Okay, probability of these particular sums of these two faces. And so that's what goes down here. We say, what's the probability that that particular sum of two faces is going to occur? So let's talk about this. What was the sum of these faces here? Each roll was a sum of 3. Okay, good. Now, how many different combinations could we have? 36. So out of 36 different combinations, how frequently does a sum of 3 occur? 2 times. So the sum of 3 occurs twice out of the 36, and I'm going to just leave that denominator or leave it and not reduce it for now because I want you to see the pattern. So I want you then now to go and figure out the probability distribution for all of the other sums. So I'm going to give you a few minutes to fill in the other probabilities. Go. Okay, so let's see if you came up with this particular distribution. You may have noticed a pattern that what was the most common sum? 7. Have any of you ever played craps in poker? What do you crap out on? I know that's in the game
7.
where you like lose out. Yeah. When do you lose out? On a 7. Wonder why? Maybe because that's the most common one. So how frequently will the casino win? The most times. See, that's why that is that case. I think it might even say doubles or sevens. I'm not sure. So see, look, then that's even much more frequently. Okay, so a couple things I want to talk about with this. Number one, what would this distribution look like?
It's symmetrical.
It is symmetrical. Very good. So if I was drawing it, you have 1 of those, and 2 of those, and 3 of those, and 4, and 5, and 6 of those, and so on. And then it's going to be symmetrical. Okay, so we know the distribution would be symmetrical. Okay. 2 other things I want us to know about qualities of these probability distributions. So fact number 1, all of these probabilities sum to how much? How much is that going to sum to? 36 out of 36, which is 100%, which is 1. So all those probabilities of a probability distribution has to sum to 1, because this is representing the population of what all the possibilities are. Every single possibility. Okay. The other thing, and this kind of seems obvious, but I just wanted to state it, you have a negative probability? No, you cannot. So no negative probabilities. Okay. So therefore, whenever we go on to the assignment on on our homework shortly, when we do pages 6 through 8, to see if you have a valid probability distribution, you should be looking for these 2 situations here, that all the probabilities will sum to 1 and that you do not have negative probabilities. Okay. All right. Very good. So now let's move on to another thing in another item in the next part of the lesson. Here we go. So back to page 3. Let's go back to page 3, and we're going to build another probability distribution. Okay? We're going to play a game. I'm going to give you all a $5 bill of Monopoly money. And so what you get to do with this is this is a $5 pays for a free stamp. So you can either have that as a bonus at the end of the unit, or it could count as one of your homework things. So you get a free homework pass right here, right now. Okay. Now, if you keep this, I'll be coming around stamping you shortly if you end up keeping it. We're playing the game today. You're not going to keep. It's not like Bowden Bucks where you're going to keep these till the end of the whatever. Okay. So everybody's got their $5. So I want you right now to read the rules of the game, and then we're going to talk about. So I want you to understand. Here's the rules. Read those to yourself so that you can decide if you want to play the game to increase your number of stamps. Okay, read that to yourself. Go. Every time the game is played, I put the cards back. So that means each play is what of the other plays? Independent. Yep. Okay. So you have to pay $5 to play the game. If you draw the ace of hearts, then I will. So you're going to give me $5. I will give you back 100. So you just made a whole bunch of money. You made $95 more than what you already had. For any other ace, for the other aces, you get to double what you started with. You gave me 5, but I had to give you 10 back. For any other heart, how many other hearts are there besides the ace of hearts? Well, so we got this. So you got the ace of hearts here, and so there's 12 other ones. Okay? All right? So for all of those, then you just break even. You gave me $5 to play. I'll give you your $5 back. You can play again. Okay, but if you draw anything else, you lose. Okay? So let's look at this real quick. With this one, you get 100. With all of these, you get your $5 back. And then what's the other ones? So with this one, and this one, you get 10 back. 10 back. So basically, you made $5. You get okay. All right, and then look at all of those ones that are untouched. I get to keep your money for all of those ones. Okay, so let's now decide. You decide if you want to play. Ready? Who wants to play? Okay, 1, 2, 3. All right, I'm just going to do 3. I don't have time for that. So you 3 come on up, and let's see how you do. I haven't had a winner yet today of an ace. Does that mean you guys are more likely to win get the ace? Why not? Yeah, it's independent. Okay, good. All right, Eva's giving me $5. Okay, yay. Now you go. She got a 3 of diamonds. Haha, you lose. I get $5. Okay, wait, hold on. I got to put the card back in because it's got to be the same probability. Okay, so there's that. Okay, go. Harrison.
No, that one.
Okay, let's see. Ooh, it's the Jack of Spades. Nothing. Haha. I just made 5 more bucks. Yes. Okay. You're next. Let's go, Trey. Ooh, 5 of clubs. Awesome. I have won every single time today. Actually, that's not true. In third period, Justin Rockmore, he got an ace. So I gave him back $10. And then he played again, and I gave him back another $10. So he actually ended up with uh, 3 stamps altogether. Okay, so that was good for him. But everybody else lost. So we're interested in ultimately, on average, by the end of the day, how frequently am I gonna win? Because I got some, Christmas bills to pay for. So let me see if I should encourage. Should I really not limit it to 3 people in a class? Do I want everybody to play? Am I going to make money in the long run, or am I going to lose? Let's see. All right. First of all, is this considered a continuous scenario or a discrete scenario? Why would you consider it discrete? It is 3, or actually 4 possible events that can occur. So there is a countable amount of outcomes. Okay. So let's talk about, so it is discrete because it is 4 possible outcomes. 4 possible outcomes or results. Okay, so let's talk about that. So let's think. We're seeing how much is the casino going to make? That's me. That's me. So X represents the profit for me on one play of the game. All right, so let's talk about what could happen. You give me $5, and then what could happen? What's one of the things that could happen? What does it say up there? Well, let's go in order, maybe.
Okay, so we get 100.
Okay, so you pick the ace of hearts. Woohoo. So if you pick the heart ace, then I give you back $100. So that's me losing $100. And if I lose $100, I'm actually not out $100. What am I out? I'm out $95. How frequently is that going to happen? Yeah, 1 out of every 52 times on average, that is going to happen. The law of large numbers says that is so. As I play this year after year after year, many, 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 many times, I will have had to lose my $95 1 out of every 52 times. Okay, I had a couple years ago where I had like 2 or 3 winners, ace of hearts that day. But this year I've had none. Okay, so it averages out in the long run to 1 out of 52 times. Okay, let's see. What else could happen? You pay me $5 to play, and what's the next thing that could occur?
We get 10 back.
You get one of the other aces. If you get one of the other aces, I pay you $10 back. So I ultimately have what? Not lost $10. I just what? I lost $5. How frequently will I lose $5? 3 out of every 52 plays, on average, in the long run. In the long run, I know 3/52 of the time, I'm going to lose $5. Okay, what else could happen? You pay me $5 to play, but you draw what? One of the other hearts. Okay, good. And then I'm going to give you your $5 back. So essentially, I just really did what? Broke even. How frequently does that happen? 12 out of the 52. Very good. And what's last? You pay me $5 and you then pick what? Happened all 3 times today. All of the other cards besides those ones. And so I gave you nothing. And I then profited positive $5. Knowing that all of these probability distributions have to add up to 1, how many times will that happen? How frequently will I get to keep $5? 36 out of 52. How'd you come up with that? Yeah, well, these represent 16 cards. So therefore, 36 is left out of the 52. So it's 36/52 of the time I win money. Okay, so let's see. Overall, in the long run, taking all of those things into account, what am I going to average at the end of the day when we play many, 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 many times? What's my average per game played? Any ideas of how to compute that? Well, I know I'm going to lose $95 how 1/52 of the time, right? But then I'm also going to what? Lose $5 3/52 of the time. And I will break even 12/52 of the time and make $5 36/52 of the time. I'm going to add all that up and I'm going to tell you, because I'm sure you can compute, it's $1.35. So we, of course, need to know, what does that really mean? Since this class is all about context, what does that mean in context of this problem? So who told who last? I don't remember. So Evans, sorry, you're up. I don't remember what's left. Evans, tell the odds what this $1.35 means. Go. Okay. Let's see what you came up with. On average, first of all, do I profit or do I lose money in the long run? It's $1. It's positive. This is about me profiting. I make $1.35. You're losing $1.35 on average. When? Every single time the game is played, I am making $1.35 on average. Now, can that really happen? Can somebody make $1.35 on a play of the game? No, but that's the average. By the end of the day, after, in this case, 15 people have played, what's my average per person profit? Okay, my average, well, that's how much I profited, but my average per play is $1.35. And so then what I actually then make would be 15 times that, which is 20 something, whatever. Okay? So on average, I will make $1.35 every time the game is played. Okay, is that $1.35 actually even a possibility on a gameplay? No, it's not a possibility, but it's okay to say this because it's a what? An average of what happens. Okay, very good. Now, this is interesting. I want to take a look at what this probability distribution looks like. So let's actually think of this. Pretend like this is 0, and we'll go by 0, 5, 10, or whatever. -5, and then all the way down, all the way down. And guess what down here is like? -95. Okay, let's look at this probability distribution. I've got just one of those. So I got one. I'm going to make a histogram. I got one little bar there at -95. I got 3 little things at -5. So 1, 2, 3. I've got 12 things at 0. So there's that. And I've got 36 frequencies at $5. Okay, so it's got to be 3 times that. All right, so look at this. What is the shape of this distribution, probability distribution? Skewed left, okay. Now, where did we just say the average was? $1.35. So the average is located here. So talk to me about the spread of this. We have a lot of it right here, but because of this outlier way down low, tell me what that does to the spread, to the standard deviation. Makes it what? Bigger. Because this is an outlier, this is what makes gambling appealing. That outlier that makes it high risk, high spread, large standard deviation. So we're going to now go down here and compute that out. I'm going to, instead of going through the formula, I'm just going to easy cheaty way you through it. And so we're going to go stat edit. So will you go to your calculator and put into L1 your X values, put into L2 the probabilities, also known as the frequencies. Okay, so go to your stat edit and put those in. They would look like this. Okay, I'm going to shortcut it. I have done that. So I've got this typed in there. So we're going to now stat. Well, I can go ahead and stat edit and show you. I have them in there. Mine are backwards. Okay, but here let's calculate. We are going to calculate the one variable, our random variable, statistics. Okay, the catch, so if you pull this up, some of you who have a menu, you have the more up-to-date operating system, the first thing of your menu says X, and you have L1 there. So those of us who don't have a menu, we put second number 1, and that's L1. If you have a menu, what does your menu say next? What's the second line in your menu? Frequency. How frequently are things happening? Where did I put those frequencies? L2. So you have to do second 2 for the L2. I don't have the menu, so I put a comma, second 2. So I have L1 with L2's frequency. If you leave that L2's frequency off, you will compute wrong probabilities because they won't be at those probabilities. So then I hit enter, and look, lo and behold, what's X bar? X bar is the mean of X, and that's $1.35. Dun, dun, dun. Notice this standard deviation is really big compared to that mean. $13.80, quite a bit of spread. So I could, like, $1.35 plus 1 standard deviation, I'm making lots of money. Minus 1 standard deviation, I'm losing money. So sometimes I'm losing money. Why is there no S of X? S of X represents a sample. But what do you know about the total of our distribution? All of these totaled up to what? Hence, the entire population of probabilities. Therefore, that's why this is sigma, because it's all the possibilities. This is the whole population distribution. All right, so very good. So that came out to $13. So the sigma is $13.80. So now you know how to get the mean and the standard deviation with the easy cheaty way. On your homework, you'll just have to mostly make these probability distributions and then compute that, okay? I've got just a couple of minutes left, and so I'm going to start this problem here because this is eventually where we're wanting this to go. We have the mean of $1.35, and we have the standard deviation of 1380. So let's draw a normal model real quick of that. This is a normal model of the average profit per play. Okay, the average profit I make per play by the end of whatever. And what we're going to do tomorrow for you guys, and actually when you leave, I'll finish this out. We're going to compute the probability. How frequently do I make a profit? Okay, so that's what we're going to look at next. So for you guys, page 6 through 8 is your homework, and I'm going to have you work on that. We'll continue that normal model problem tomorrow. Okay? All right, so let's go ahead and come up with these amounts. I know that here's my $1.35, and then I would add up a $13.80 each standard deviation. Okay, and then I'm going to subtract down $13.80 each one of these. So there's quite a bit of times that I am losing money. Okay, but if I want to know what proportion of days do I make a profit? At the end of the day, what proportion of days do I have an average profit per play? Okay, so this mean right here is at $1.35. So okay, I'm definitely profiting on all of these days. I'm definitely, when those are averaging, I'm profiting. Okay, when do I start profiting? When my average is what? When my average is $0 or more, I make a profit. So how do I compute the proportion of days that I average a profit every play? And that is this area here. So I want you to compute this area here. So you're going to be doing your z-score. And so our x is break even, and that was our 0. Okay, so 0 minus the mean over the standard deviation, and that comes out to negative 0.098, I think. And so we want to norm CDF from that negative 0.098 up to 99. And we get about 54% of the days I will make a profit. So is this good? And that answer is yes. Anytime I am profiting more than half the time, in the long run, I'm going to be a winner. And the casino, me, whoever it is, the one taking the money, I'm going to be winning. So you only win 46% of the time, all right? So that's what happens is we can take a discrete event and find its mean and standard deviation, to then turn it into a continuous situation. So I can then turn it into continuous. This is going to lead us into our next topic in chapter 18 on sampling distributions. Anyway, so I want you to remember this situation so that in the future we can talk about it. Taking our discrete situation, making it continuous so we know its shape, and then we can compute with normal model probabilities. All right, so pages 6 through 8 today are what you are going to work on your lesson in your packet.